In this video, we will find the z transform of x of n, and x of n is given in this expression. So let's try to find the z transform. First of all, let me write the expression for the z transform. X of z, which is the summation from n minus infinity to plus infinity, x of n and z of minus n. So we have to evaluate this summation, which defines the z transform for the discrete sequence x of n. Now here, let's try to see what our sequence is actually and where it is non-zero, because you can see u of n minus 1, which has certain limits. It's not available for n minus infinity to plus infinity. Rather, we have to look at the limits, because the limits of n, which is from minus infinity to plus infinity, will be modified by this u of n minus 1. So let's try to find out this u of n minus 1 first, so that we can modify our limits according to the unit step function, which is the shifted and inverted version of the unit step sequence. So let's see what's u of n first. As you are familiar with u of n, u of n is actually a discrete time signal, which exists from 0, 1, 2, 0, 1, 2 and onward. So this is unity here. This is by definition the unit step sequence is given in this form. Now if we have u of n minus 1, it is just a delayed version of the unit step sequence by 1 unit. So if I draw it here, I would draw my u of n minus 1 as this one, 1, 2, 1, 2, 3. So it's delayed or moved towards right, dragged towards right by 1 unit. Now we have u of minus n minus 1. So in the next step, let me plot u of minus n. U of minus n minus 1 is the mirror image of this function, u of n minus 1. So how the mirror image would look like? You can see the mirror image would look like this. This is still n axis, and u of if I just take the mirror image, it's minus 1, 1 at minus 1, similarly at minus 2, minus 3, and so on. Okay, so these are now you can see it goes on. So this is the sequence from minus 1 up to minus infinity. It means that a minus a raised to the power n, u of n minus 1 will only be available for n minus infinity to minus 1. So we would modify this the summation. We would modify the limits of summation, the upper and lower limit of summation of x of z according to u of minus n minus 1. So let me rewrite this expression now. So I would rewrite x of z, which is the summation n minus infinity to plus infinity, x of n and z of minus n. So I just substitute x of n here. I can rewrite it as n minus infinity to plus infinity. Let me rewrite x of n. So I'm just rewriting x of n here, and x of n is minus a raised to the power n u of minus n minus 1, and then we have z of minus n. In the next step, what I can do, I'll just rewrite it, but now I'll apply the limits according to this function, and this will not appear in the next step. So we can rewrite our limits for n minus infinity to minus 1, because this whole product is non-zero only for n minus infinity to minus 1. The reason is this function is only available for minus infinity to minus 1, so it is non-zero only in this range. So we can rewrite it as minus the summation of minus infinity to minus 1, and the negative sign I would just write outside the summation, and here you can write a raised to the power n z of minus z raised to the power minus n. Now in the next step, what we can do, well, let's just try to make it try to make one substitution for the variable. We can take a variable m equal to minus n. This is just to change the summation of minus infinity to minus 1, to change it to 1 to infinity. Okay, so this will be m equal to my plus infinity to plus 1, right? And a raised to the power would be, just keep this in mind, a raised to the power would be minus m now. Okay, and z raised to the power would be m. Okay, so we have modified this n and minus n according to this variable. N and minus n are modified according to these variables. Now what we can rewrite it in this form. We can just say, okay, our summation is same as m. We can rewrite this summation as 1 to infinity a raised to the power minus 1 and z whole raised to the power m. Right, so this is our x of z. Now x of z converges only if a minus 1 z, if the absolute value of this is less than unity. Okay, then x of the z transform converges, and it means that the absolute value of a inverse and the absolute, we can just rewrite it like this. Okay, and we can also just say that z is less than 1 over a inverse. Okay, from this inequality, and we can say that z is actually less than a, the absolute value of a. So you take it in the numerator and change the sign of its power. Now z, this would give us the region of convergence. The z, the absolute value of z is less than the absolute value of a. Now we can find this x of z. We already have the compact form of this one, this summation, and x of z can be rewritten. We can rewrite x of z as in the closed form of this sum, which is 1 minus a inverse of z. Keep this, I hope you are familiar with this formula. Well, we cannot apply the formula yet. Let me explain a couple of things more, because we cannot directly apply a formula. There is a negative sign outside the summation which we forgot. I forgot this sign, and also the summation is from m1 to infinity, and the formula for is, let I'll do this step once again. Okay, we cannot apply this formula right now, we have to make some changes here. So the summation, actually the formula is given, for n0, the variable 0 to infinity, if you have r raised to the power n, and this r is less than 1, then you can write this summation as 1 over 1 minus r. Okay, you can write this summation in this form, but here we have m1 to infinity, so this is the problem. We have to we do not have the term of m equal to 0. Okay, so we need the term for m equal to 0 in this summation. Then we would be able to apply the formula. And how we can do that? We can do just, I'm just rewriting it here, minus sign outside the summation, and m1 to plus infinity a raised to the power minus 1 and z raised to the power m. Now what we can do, you see what is the term which is for m equal to 0 in this summation. M equal to 0, if you substitute m equal to 0, then this would be a raised to the power minus 1 raised to the power 0 is actually equal to 1. So it means a 1, keep in mind a negative sign is outside, so there should be it's actually a minus 1. So a minus 1 is missing, in this summation, and we can actually add and subtract a 1 before applying this formula which we have written here. So let me add and subtract a 1 to this summation. So I'll write z 1 and 1 add and minus 1, and then we have a summation m1 to plus infinity a raised to the power minus 1 z raised to the power m. Now this one we can combine here in this summation, and we can write it as 1 minus 1 plus sum m1 to infinity a raised to the power minus 1 z whole raised to the power m. Now you can see 1, we can rewrite it as 1 minus the we do not need this bracket now, 1 minus the summation now this is important, just note it down here. M is from 0 to plus infinity now. Okay, from 0 to plus infinity, m0 is equal to 1, which we already added to this summation. So m is from 0 to infinity, and m is from 0 to infinity, and a raised to the power minus 1 z raised to the power m. So let's try to simplify it further. So if I simplify it further, it would be 1 minus, now this is summation is in the same form. We can apply that formula which I just explained above. So we can write it as 1 over 1 minus a raised to the power minus 1 whole a raised to the power minus 1 times z. So this can be further simplified, and we can write it 1 over 1 minus z over a, right? And you can just rewrite this one. Let's try to simplify this. 1 minus a over a minus z, right? Or you can write it 1 minus a over 1 plus a over z minus a. Okay, we just take a negative common from this, so it will be z minus a, and it will change this sign to plus. Okay, so we can rewrite it in this form, and this can be written as z minus a and z minus a plus a, which is z over z minus a. So we can see that our x of z, the z transform, is z over z minus a. Now this is the z transform of the discrete time sequence minus a raised to the power n u of n minus n minus 1, and with the condition that the absolute value of z is less than the absolute value of a, and just I explained earlier. Now you can find the region of convergence. Okay, the region of convergence of from this expression x of z, and the region of convergence is can be found using this information. Okay, so if you see the z plane, where we have the imaginary part of z here and the real part of z here. So what we can say, we can identify immediately the poles and the zeros of this function. So to find the zeros of the function, to find the poles of the function, we equate the denominator, which is z minus a equal to 0. Z minus a equal to 0. It implies that z is equal to a is a pole. So if we have an a here, suppose this is a, so this is a pole. And if we want to find the uh, zeros, we just equate the numerator, right? So we can equate the numerator, which is this one, equal to 0. So z equal to 0 actually gives you the 0 of this function x of z. And from this condition, the absolute value of z less than a means that the region of if I draw a circle with a radius equal to a, something like this, so the absolute value of z less than the absolute value of a will be this region, which I let me make it will be this shaded portion. Okay, it will be this shaded portion. It will not include the pole because the absolute value of z is less than the absolute value of a. So this shaded region gives us the region of convergence. So this is our ROC, okay, region of convergence.